In this section, we use the linear combination of atomic orbitals method that we use to understand bonding to also understand the band structures in insulators and semiconductors. Recall that we can describe the wave functions possible in a chain of atoms as a wave of atomic wave functions. Mathematically, we can describe each of these wave functions with a k-vector which defines the envelope of the wave function. For the most bonding wave function, the wave vector k is a constant, giving us simply a sum of the atomic orbital wave functions. As we move higher in energy, the wave vector k increases, giving us more curvy envelope functions, with the most antibonding wave function having the most curvy wave vector, that is k equals pi over a. All of these wave functions can be described as the product of the envelope wave function with wave vector k and then the sum of the individual atomic orbitals that looks like the k equals 0 wave function. The kinetic energy of the overall wave function, which depends on the second derivative or the average curviness of the wave function, will clearly depend on two components, the most important of which is the curviness of the atomic wave functions that make up the overall wave function. Well, we already know the curviness or average kinetic energy of these wave functions as the energy of the atomic orbitals. The envelope wave also adds some additional energy to the wave function. That comes from the e to the I kr part of the overall wave function. Thus, we expect the energy of all of these wave functions to be similar to the energy of the constituent atomic orbital, plus or minus an energy due to the wave vector of the envelope function. We can make a good estimate of the energy of these wave functions, making a few approximations based on our knowledge of the atomic orbitals and their bonding with neighboring atoms. We first approximate the block wave function by moving the e to the I kx into the summation, where instead we use r, the position of the atom. Then we are going to assume that only nearest neighbor atoms have interactions worth worrying about. Our atom then at position I will interact only at position I plus 1 or position I minus 1, and all of the other atoms 2 or more atoms away aren't interacting significantly. So for example, the Hamiltonian operator between two neighboring atoms, Hij, is non-zero, whereas it will be equal to 0 for all atoms further than one atom away. For simplicity here, we will even ignore the overlap integral s between neighboring atoms. This leaves us with then only three non-zero quantities: the normalization condition of an atomic orbital, the Hamiltonian of neighboring atoms, which will be equal to the interaction potential or bond integral, and the Hamiltonian of an individual atomic orbital given by its energy. Since our specific example here is a chain of s states, we have the energy of the s states and the sigma bonding interaction between two s states for the bond integral. Like we did before, we will set up a series of equations using the Schrödinger equation applied to our block wave equal to 0 that we get when we integrate with each atomic orbital. Because only nearest neighbor interactions contribute, for our atom at position j, we only have to worry about the atom at j, j minus 1, and j plus 1. Thus, only three terms of our block wave function k matter, and we can write this equation in three parts. One at position j minus 1, the position at j, and the position at j plus 1. The atom at position j minus 1 is a near neighbor atom, such that the Hamiltonian between a near neighbor atom gives us the bond integral VSS sigma. The psi j e psi j minus 1 term gives us a term proportional to the overlap integral, which we are setting to 0 for now. Then the wave vector e to the I k dot the position of the j minus 1 atom, we can change to e to the I k times the position of the jth atom minus a, where a is the distance between atoms. For the term involving the jth atom itself, we have psi j, the Hamiltonian of psi j, which is simply the energy of the atomic orbital. And then psi j, the E comes out, and we have the normalization condition, giving us ES minus E times the wave vector e to the I k at Rj. The other neighbor at j plus 1 gives us a similar contribution, including the bond integral VSS sigma again, as we had before. But this time the wave vector part turns into e to the I k dot Rj plus a, the distance between atoms. Now, because this entire equation is set equal to 0, we can divide each of the terms by e to the I k dot Rj, which will remove this term and the Rj parts of the other term. Thus, I get ES minus E plus VSS sigma times e to the minus IKA from the one side plus e to the plus IKA from the other side. We then recognize that by converting this exponential into cosine plus I sine will give us 2 times cosine of Ka. Now, if we wanted to keep terms that were small, we could write all of these equations in matrix form and have a computer solve them. This is known as the tight binding approximation for calculating band structures. Now we have a dispersion relation for the energy of our block wave functions as a function of the wave vector of the envelope function. This gives us a so-called band of wave functions that has wave vector between minus pi over a and plus pi over a. The energy of all of these wave functions is approximately the energy of the atomic orbitals used to make the basis. Then the energy varies depending on the k vector, which determines how much bonding or antibonding interactions exist between neighboring atoms. For this chain of s atomic orbitals, the k equals 0 state has the most bonding. Because each atom has 2 bonds, the energy of that state is the energy of the atomic orbital plus 2 times the bond integral. For k equals pi over a or minus pi over a, the wave function is most antibonding, and so the energy is the energy of the atomic orbital minus 2 times the bond integral. Remember that our bond integral for s-state atoms is less than 0 because there's bonding interaction between neighboring atoms at k equals 0. However, if we made a chain of p states aligned along the direction of our k vector, then our neighboring interactions would be in antiphase or antibonding. This tells us that the bond integral between sigma bonded p states is greater than 0, meaning the bands would run down from k equals 0 instead of running up from k equals 0 as they do for s states. The cosine Ka dispersion relation we derived tells us that near k equals 0 we should expect a parabolic type dispersion relation. However, it also tells us that at another region, perhaps at k equals pi over a, the dispersion relation might be parabolic but pointing the other direction. Because all of our bond integrals depend on the Coulombic potential of neighboring atoms, it turns out that all of the bond integrals will depend on 1 over d squared, where d is the distance between the 2 atoms. Thus, 2 atoms closer together will have stronger bonding that will be apparent in their band structures. In general, we expect most crystalline materials to make electronic structures based on their atomic orbitals, and that these atomic orbitals will interact with each other and form bands that might either run up or run down from k equals 0, which we call the gamma point in the Brillouin zone. We can also expect that at the extreme points of lowest energy or highest energy, that the bands will have generally a parabolic type dispersion, where that parabolic dispersion might be pointing up or pointing down. We expect that materials with a large bond integral due to a large orbital overlap will have a large dispersion, meaning there's a large band of energy from the most bonding state to the most anti-bonding state. In contrast, a structure with small orbital overlap will have a narrow band of allowed energy states. Because the total number of states depends only on the number of atoms, this generally translates to narrow bands having a higher density of states, where by density of states we mean the number of states per energy.